Swayam Prabha. Digital India. Educated India.
I think let's go straight now to the next presentation. This is from Professor Cheng Liang Chen, also a well-known figure in the space of process systems engineering from the National Taiwan University. He will be presenting on methanol as the hydrogen carrier to approach the sustainable low-carbon energy system. Prof. Chen, over to you.
Good morning, ladies and gentlemen. This is Chen Liang Chen from National Taiwan University. Ms. Ka-Xin So is the main contributor of this work. Here's the topic today. And today I will talk about the renewable energies and hydrogen, methanol, and some economic evaluations. And, but at first I would like to talk about the work, energy consumption and CO2 emission. And as we can see, that during the past 50 years, the world energy consumption increased by almost 4 times. Among them, we can see that more than 80% comes from fossil fuels. If we look at electricity, then more than 60% of electricity of the world comes from fossil fuels. So that's why during the past 50 years, the CO2 emission increased by almost 3.3 times. So under such conditions, that our target is to the net zero emission by 2050. So it's a challenge problem. We will look back to Taiwan, the energy situation in Taiwan. More than 95% of the primary energy is imported. And among them, 87% of the energy comes from fossil fuels. And 66% of the primary energy is used to generate electricity. So under such conditions, how to reach the net zero emission in the near future is the first method is the full electrification, and the second is the full renewables. Of course, it's a very, very challenging problems. So during the plan, we can see that we have the, I think we have the 60 gigawatt wind power and 85 gigawatt solar power in the near future, based on the current plan. So, hydrogen is primarily the battery is running out. Not mine, the computer. The battery is running out. So in this case, hydrogen is an energy carrier of intermittent renewable energies, because the renewables will take about 65%. So the problem is a high percentage of intermittent renewables. What have happened? So renewables, of course, it can directly provide electricity to the public grid. But due to the intermittent characteristics, and so we need some suitable carriers to store surplus renewables. And to store surplus renewable energies and provide additional electricity in deficient situations. So further to the pump hydro and battery, I think that green energy from water electrolysis has been accepted as the effective low carbon energy carrier. However, renewable energy and green hydrogen will remain insufficient in some locations due to then wind farm constraints, like Taiwan. It's a very, very small island. So it's impossible to provide all renewable energy by ourselves. So we need a hydrogen value chain. So an international supply chain of renewable hydrogen is required. And so we have to build a green hydrogen value chain for long-term and large-scale storage and transportation. But we can know that Taiwan or Japan or even Korea is different to Europe. So it's a great challenge for long-term transportation and large-scale storage. So the pipeline system is almost impossible for Taiwan or Japan. So we need some chemicals to store large chemicals, energies. So two chemicals are under consideration. One is ammonia, and another is methanol. But if we compare the process of the synthesis and the liquefaction problem, and the storage and transportation problem, and the cracking and reforming problem, we can see that methanol and ammonia have different characteristics. So ammonia may be a low carbon hydrogen energy carrier because no CO2 is involved. But methanol may be an energy saving hydrogen carrier. But in the meantime, we have to consider the CO2 capture, transportation, and storage problems. So here is the proposal. So at first, the hydrogen, the electricity should go to the grid at first, and then the second choice is the pumped hydro and the battery, and third is the electrolyzer to generate the hydrogen. But suppose the hydrogen is going to transport far away, so some of the hydrogen can be synthesized into the methanol, and then shipped to other place. For example, from Australia to Taiwan, it takes 1 week. From Qatar to Taiwan, it takes 2 weeks. From America to Taiwan, it takes 1 month. So the shipping problem is very, very important. And we can store a large methanol in the import countries. And then suppose we need the hydrogen, we can use the steam reforming process to generate the hydrogen again and capture the CO2 and shipping back to the exporting country. So here's a proposal. So here are critical steps concerning the low carbon renewable energy supply chains. And the key point is the methanol synthesis and methanol reforming. So here is one possible process, the proposed process. So the hydrogen and CO2 can be synthesized in the methanol reformer. And here are the separator and gas liquid separator and liquid separator. So we can generate a very pure methanol for transportation. And I would say that a better process are in progress. And here is the one possible process for methanol reforming. So for the importing country, the methanol can be based on the steam reformer and water gas shift reactor to generate the hydrogen and the CO2 again, and use the MEA to absorb the CO2 to generate high purity nitrogen, and then we can capture the CO2 in a liquid state so it can send back to the exporting country. And here are some details about the cost of each steps. So as we can see, the basis is 1 ton methanol. So we take this amount of the electricity for electrolysis to generate the hydrogen. And the money is $68.5 US dollars. And then the cost of the synthesis and the cost of the transportation of the methanol. And here's the cost of the methanol reforming. And as you can see, that the cost of separation of hydrogen and CO2 is quite high. And here's the cost of liquefaction and the transportation of CO2. So, and based on this hydrogen, we can use some fuel cells, for example, and to generate the electricity in the importing countries. You can compare the electricity of the here in importing country and electricity from the exporting country. So they are quite different. So it costs a lot. So concerning the cost, it takes the basis is 1 ton methanol. So 232, the cost is to handle this value chain by methanol. And 280 is the cost of the electricity in the importing country. I forget to mention that I suppose the renewable energy price in the exporters is $30 per megawatt hour. And so here's the cost of 512, and here's the cost of the electricity for 1 megawatt hour in the importing country. Okay, so here's the cost, $30 in the exporting country, and here's the cost in the importing country. So it's quite different. And suppose the renewable energy prices are different, so we can find a different electricity price in the importers. Okay. So here is, we can look at the cost of the supply chain again. We can see that the cost here in the importing country, concerning about the methanol reforming and the gas separation and the CO2 degradation, it takes a lot of energy. So another project is to reduce the cost here. So our method is to use the oxy-combustion methanol-fired power plant, and CO2 is captured in liquid state in the meantime. Here is the power plant. So the working fluid is the CO2, So here's the liquid CO2. And liquid CO2 can mix with the pure oxygen. And here's the gas phase, the CO2, high pressure, 300 bar. So the turbine can generate electricity. And we can remove the water, and obtain the high purity CO2 again, and compression, and then with chilled water. So in that case, it will become the liquid phase. So in that case, extra CO2, liquid CO2 can be removed. So it's a carbon capture directly. And the other liquefied CO2 can separate and increase the pressure again. So here is the oxy-combustion methanol-fired power plant. So in this case, we don't have to use the methanol reforming and additional independent step for carbon capture. So in this case, we can reduce the electricity price in the importing country. So I would like to take a conclusion because time is limited. And so in this work, we use the hydrogen as a carrier of renewables, and methanol is a hydrogen carrier. So in that case, we can deliver energy from exporting countries to their end users. For the exporting country, for Taiwan, exporting country means Qatar or Australia. Okay, and the overall cost of utilizing methanol is hydrogen carrier. You can see from here, for each ton of methanol, it takes $232 US. And for 1 megawatt hour in importing country, we need 2.5 megawatt hour of renewables in the exporting countries. So if the price of the renewable energy is $30 in the exporting country, then the cost of the electricity will be $136 in the importing country. And the methanol-fired oxy-combustion power plant has changed to reduce 50% cost. So here are my students. Thank you.
Thanks, Prof. Chen, for sticking to time, taking us back at least to our trajectory. Any question for Prof. Chen? One question? Two? I'll take one from...
François Maréchal, EPFL. You have not considered electrochemical systems for converting methanol into electricity in fuel cells, for example. Direct methanol is one of the options, no?
Another chemicals?
Yeah, no, so converting methanol into electricity with an electrochemical systems like a fuel cell.
Yeah. No, in this case, I count the efficiency about 60%, but not the details in the future.
But Well, you can reach higher efficiency if you go to electrochemical systems, right?
Yeah, it's possible. It's possible. Yeah.
Okay, thank you very much for the question. Or maybe just one more.
Prof. Chen, a nice presentation. So have you considered, so I have two questions, right? The first of all, do we have fuel cells, the capacity, the scaling of fuel cells that will be able to supply the electricity demand of, let's say, Taiwan? I mean, do we have that scale up that is needed for fuel cells? That's first question. The second question is, have you compared with MCH, methyl cyclohexane? Because that's liquid in both sides. And so how does methanol compare with that?
Okay. So thank you for your question. The large-scale fuel cell is possible because the operation of the large-scale fuel cell should be easier compared with a typical power plant. But we are still waiting for the mature of the system. So I'm concerned about another chemicals. Other chemicals, I forgot the name, is considered in Japan. But in my opinion, the molecular weight of that chemicals is very, very high. So for the per unit weight, the amount of hydrogen that can be carried is too small. So I.
But in hydrogen transport, it's the volumetric density which is more important than weight. So if you compare
The volume, yeah. But I still remember that the molecular weight of the hydrogen, something that toluene is more than 60. Yes. So I can't remember the density, but the efficiency and the reforming, the temperature is very high. I still remember that it's almost 800 degrees Celsius. So I don't know. We can compare it, but it's a patent. It belongs to one company in Japan. Yeah. It's a secret. So, thank you.
Thanks, colleagues. Okay, I think let's give Prof. Chen a round of applause.
Thank you, Maurice. Thank you.